Chapter 4, Section 4, Radiation from Individual Atoms. Both solid matter and dense collections of atoms emit black body radiation, but gases generally behave differently. All right. That's the important thing right here that we're looking at. Um, as they radiate, solids radiate, and it goes on to talk about an incandescent light bulb and the light that is emitted, or that spectrum that is emitted from a filament in a light bulb, and how it relates to Vin's law. Um, Other types of lights, that's just the light with a filament in it. Fluorescent lights, neon lights, they all work different. They work a little bit different, okay? And it says right here, however, fluorescent lights um, and neon signs are not black bodies. Remember, for it to be a black body, it has to have a lot of atoms close together, a lot of those particles close together, where gases do not. Remember, gases are spread out. Okay, they instead produce a light by first pulling electrons free from the atoms and the gases, which then emit light when the electron is recombined. So let's take a look at that, and then we're going to watch a little video on a light filament. So we've already been looking at this hydrogen atom. We've been looking at the hydrogen atom, and I'm going to show you what it means by the stripping away of the atoms. So what happens is they're hit with a large amount of energy. And we've learned that the electron is now shot off and ionized. All right. So we're going to do this again. And what happens here is when the electron flies off and the atom becomes ionized, what's going on is when this happens with a bunch of these hydrogen atoms at a time, or we'll say fluorescent atoms, whatever kind of a gas you're talking about, is it's going to hit it. Boom. It's going to be ripped away, where the atom becomes ionized. When one of the electrons from another ionized atom comes back to us here, didn't work quite the way I thought it was going to there. Let's see. Boom. There we go. When this electron comes back, it will drop down and give off light. So give off that photon. And that's what that's what we're looking at. Okay, that's the way it's working in a gas. When it picks up this electron comes back. If it is in a try to get it to come back in a further away. I don't remember what combination I just used, but there we go. Anyway, you can see, boom, it's giving off light. All right. It works different in a black body, like a light bulb filament.
As objects become hotter, two things happen to the light that they emit. The first is that they start emitting more light at every wavelength, at all the different colors at which that object emits. It gets brighter. The second thing that happens is that the peak of the emission shifts from the red all the way up through the blue. It goes on even further than that if they get hot enough. So in other words, the object changes color. You're a little bit familiar with this if you've ever used a Bunsen burner, because the flame on your Bunsen burner was blue in the middle and it was red on the outside. And if you wanted your chemistry reaction to go fast, you stuck the bottom of the test tube down in the blue part of the flame, because that's where the flame was hotter. And if you wanted the reaction to go slow, you stuck the bottom of the test tube in the red part of the flame, because that's where the flame was cooler. I have here an incandescent bulb that I can use to demonstrate this same effect. Now I'm going to point out that we have two cameras. One of those cameras is fitted with a filter that just filters out some of the light. So when you see the light bulb through that camera, it's going to look fainter so that you can actually see the color better. But the other camera is going to show you the change in brightness a little bit more clearly. So I'm going to start by turning this giant dimmer switch just a little bit so that there's a little bit of current running through the light bulb, and we'll see that it lights up, and we'll take a look at the color. So here the light bulb is barely lit, and you can see that it's red-orange. It's a very reddish color. This is almost exactly the color of Betelgeuse, one of the stars in the night sky. If I add more current so that the filament gets hotter and hotter and hotter, you can see that the red goes away and the color becomes dominated by yellow. If I continue on and I go past that point and I keep heating up the filament hotter and hotter and hotter, you can see it gets much, much brighter as it gets hotter, but then it also turns bluer as it gets hotter. Until here, this is as high as I can go with this particular light bulb, and you can see that the color of the light bulb is definitely bluish, and it's extremely bright at this high temperature. So this is something that you should look for when you look at stars in the night sky. You should look up into the night sky and see that some stars are reddish, like Betelgeuse is reddish, and some stars are bluish, like Rigel, also in the constellation Orion. Stars are red or they're blue because they're different temperatures. So cooler stars around 2000 degrees Kelvin are redder, or hotter stars around 10,000 degrees Kelvin or even hotter than that are bluer. And sometimes they emit even into the ultraviolet or into the X-ray when they're very, very hot. This might be a little bit confusing to you, that hotter things are bluer and cooler things are redder. And that's because you're used to plumbing. In plumbing, what the plumbers do is they use blue for the cold tap and red for the hot tap. But that's just because of a physiological reaction of your body. So fair-skinned people, if they've been outside running around in the sunshine and they're all heated up, their skin turns bright red as the blood rushes to their skin. And then they can turn blue with cold in the wintertime when it gets really frigid. And so plumbers are responding to the humanness of your body and the way your body responds to hot and cold. And in science, and especially in astronomy, it's exactly the opposite. Blue things are hot and red things are cold.
All right, so let's take a look at what this means with a Bunsen burner. So here's a Bunsen burner. And at the top of this Bunsen burner, we see that little orange wisp, that yellowy orange or reddish orange wisp. And what's going on with that? That is the carbon atoms in the air going, showing us emissions. This, the blue part, is the gas. It's the carbon atoms in the gas. And this is working more like this did. All right. So this is working more like this, whereas the little orange wisp on the end of it, the little, we'll just call it orange, that little orange wisp is more like the filament in a light bulb. Okay. So the blue part is the carbon gas going through this loss and gain of electrons. And if we take different elements and put them in that flame, this right here is copper, and the copper sulfite is going to turn it, the flame, green, whereas strontium, on the other hand, will turn it red. And it does this because of the electrons moving back and forth between the orbits. All right, they have different numbers of electrons. They have more protons, different electrons. Therefore, they're going to give off a little bit different shades of color. Next, we go over the chemical elements. Now, the chemical elements, all this little section is right here, is a refresher course on protons and electrons. All right. For example, hydrogen consists of, I highlight that. For example, hydrogen consists exclusively of atoms that contain one proton. helium of atoms that contain 2 protons, carbon 6, oxygen 8, and so forth. Although the identity of an element is determined by the number of protons in the nucleus, the chemical properties of each element are determined by electrons. However, the number of electrons normally equals the number of protons. All right. Protons attract an equal number of oppositely charged electrons until the atom is electrically neutral. Hopefully you remember how to get a neutral atom. You just add the number of protons and electrons, and that charge should balance out to 0. Now, here are some of the elements we've been talking about. Hydrogen, helium, here's the number of protons, and usually the number of electrons also. Neutrons, again, can vary, and when we have a variant of neutrons, it is an isotope. We call those isotopes. Electron orbits. All right, electron orbitals or orbits. The most important effect is that electron orbits may only have one certain prescribed size. Okay, so it's not like these orbits are all different sizes; they're prescribed sizes. And although I have it highlighted here, although a planet may orbit the sun at any distance, an electron may orbit in an atomic nucleus at only certain distances. Much as when you climb a set of stairs, you can only be only at a certain discrete height or an only stair. There's no like half stair. It's a stair. All right. And basically what this is telling us is in this image here, in this model, I can hang out. These electrons can hang out in these orbits. Okay. They can hang out in any of these, this hydrogen. But these electrons can't hang out right here. They have to be in one orbit or another. There's no place in between for them to hang out. They move so fast from here to here, it's ridiculous. All right? We're talking speed of light, man. They're moving fast. And there is no place for them to hang out in between. They have to be on an orbit. Okay? This is called quantization. We describe this restriction on the allowable size and orbit of orbits by saying they are quantized. The restriction on orbital sizes results from the electrons acting not just as a particle, but also as a wave. That is, just as light itself has a wave-particle duality, so does an electron. The electron's wave nature forces the electron to move only in orbits whose circumference is a whole number of wavelengths. If it were to move in other orbits, the electron's wave nature would cancel it out. All right. Now, as we move down here, the wave nature of the electron has another important effect. It smears out the location of the electrons. As a result, although we have described the electron as orbiting like tiny planets around the nucleus, most scientists prefer to think of them as existing in an electron cloud, which is called an orbital. You guys remember the electron cloud, all right? We can either tell how fast they're moving or we can tell exactly where they are, not both. Now, this just goes on to explain the electrons and their orbits, and it summarizes this way. In summary, then, atoms consist of a nucleus containing protons and neutrons surrounded by electrons in orbitals. The identity of the atom, the element, is determined by the number of protons in its nucleus. The electrons are bound to the nucleus by the electric attraction between protons and electrons. Electrons may shift from one orbital to another, accompanied by a change in the atom's energy. With this picture of the atom in mind, we can now turn to how light is generated in an atom. All right, generation of light by atoms. Now, remember the conservation of energy, and that's what this revolves around. Although the energy of an atom may change, the energy cannot just disappear. One of the fundamental laws of nature is the conservation of energy. This law states that energy can never be created or destroyed. It can be changed in form, though. According to this principle, if an atom loses energy, that energy must reappear in some other form. And one important form in which the energy reappears is light, or more generally, electromagnetic radiation. If you've been working on your lab, we know this. Here comes an absorption. It absorbs that energy. And when it releases that energy and the electron drops down in orbit, it gives off light. In this case, it will give off an electromagnetic pulse that is purple, a purple color. Okay, bluish purple. Boom. All right, yeah. Let's see what happens now. I'm going to go out a little bit farther. And when it drops down, it's going to give us a little bit different color light. Remember, long wavelengths, if we put it out here, our wavelengths are going to be what? A different color. All right. They're going to be different colors because they're dropping different distances. So it's going to give us, and that's where our spectrum comes from. So, when this reverse process, instead of it emitting light, it absorbs light, or it absorbs that energy. So it emits energy and it absorbs. Here comes another absorption. Boom, right there. And then here comes the emission. Right, it absorbs and it emits. It'll absorb, boom. And then as it drops back down, it will emit. All right, absorption is when it gathers that energy. Emission is when it lets it go. So finally, in this section, emissions and absorptions are particularly easy to understand if we use the photon model of light. According to this model, an atom emits a photon when one of its electrons drops from an upper to a lower orbital. Similarly, an atom absorbs light when a photon of the right energy collides with it and knocks one of its electrons into an upper level. 4.5, formation of a spectrum. The key to determining the composition and conditions of astronomical body is its spectrum. The technique used to capture and analyze such a spectrum is called spectroscopy. And we can form that spectrum in a couple of different ways. If you've been in my classroom before and you've seen those little tubes that we held up to the lights, how they have that little slot in the end of the tube, and then you look through the tube and you can see the spectrum. This is what's going on there. It's called grating. It has a little slot in the end of that tube, and then it passes through a film and it forms the spectrum. On the other hand, you can also use a grating to just let one beam of light through and hit the prism, and the prism can also form the spectrum. All right, and here's the plot of a spectrum. Brightness is this way, and wavelength. The larger the wavelength, remember it's red. Shorter wavelengths are purple. So how is that spectrum? How is that spectrum formed? We saw earlier that each kind of atom has a different number of electrons. Remember, protons and electrons, they're different in each atom. We should know that by now. So that means that each kind of atom has a different set of electron orbitals. We also saw that orbitals in which an electron is located at any given moment sets the atom's energy. For this reason, scientists sometimes refer to orbitals as energy levels. I always called them orbitals. That's that. But when an electron moves from one energy level or orbital to another, the atom's energy changes by the amount equal to the difference in the energy between the two levels. And we already know that. Here's our energy and what's going on over here, okay? Boom, there it goes, all right? We know what's going on with that. Now, after we talk about this energy difference, this next section, this next little bit right here shows us how to calculate that energy, right? I'm not too concerned with that at this point, but we do need to know, it's leading up to this. All atoms have a different light signature. So in the previous paragraphs, we have described how atoms emit light. Moreover, we have seen that each chemical element emits a particular set of spectrum lines, and that these emission lines provide a way to identify the presence of that element in a hot gas. Now there are types of spectrum. Okay, we looked at this up here, identifying atoms by their light, and each element gives off a different spectrum. There are three types of spectra. Three types. For some sources, the brightest of the emitted light changes smoothly with a wavelength of all colors present, and that is a continuous spectrum. This is what we saw out of those tubes when we looked at the lights in my room, right? That is a continuous spectrum, one like this, continuous spectrum. Some heated objects have spectrum in which light is emitted in only a few particular wavelengths, while most of the other wavelengths remain dark. This type of spectrum is an emission line spectrum. That's this right here. That is what we're getting from this. All right, that's what we got for this. When we're shooting these in here, and it boom goes back, it gives off that color. It's going to give off a little bit different shade of a color from here. It'll give off a different shade of color from here, and so on. All right, that's what this is. These lines are what a hydrogen atom is going to give us. Those colors, those photons, those wavelengths. Now, these colors right here that it's being hit with, notice that's a purple. All right. That was a purple color. What color is this going to be? Let's see. That's a different shade of purple. Now let's check another one here. Notice it's giving off different colors as it's coming back down. All right. So an absorption is the energy that this is absorbing. It's the energy that that atom is absorption. An absorption line spectrum. It lets all of this through except these colors. Those colors, those photon, that energy, we'll say. In this case, this energy waves are what excite those electrons. A hydrogen absorbs those colors, all right? It absorbs those. That's the difference between these different spectrum. Still different type of spectrum arises when light from a hot, dense body passes through cooler gas between it and the observer. In this case, nearly all the colors are present, but light is either missing or much dimmer at wavelengths absorbed by the atoms or molecules in the cooler gas. This causes the bright background to be crossed with narrow, dark lines, where the light of some colors is fainter or absent altogether. This resulting spectrum is therefore called a dark line or absorption line spectrum. So again, continuous spectrum, emission, this is what it gives off. That's the photons it gives off, and these are the photons it absorbs. Astronomical spectrum. The first step facing an astronomer who wants to analyze a spectrum is to identify the spectral lines. This is done by measuring the wavelengths of the lines and then consulting a directory of spectrum lines. And there is a directory of spectrum lines there that you can match things up. By matching the wavelengths of the lines of interest to a line in the table, astronomers can determine what kind of atom or molecule created that line. How does this work? If we look down here, let me highlight that real quick too. Let us now apply what we know. And here are the different of our sun, compositions of stars like our sun. All right. Let us now apply what we know about spectra to astronomical bodies. We begin by using a telescope to obtain a spectrum of the object of interest. Next, we measure the wavelengths and identify the lines. And as an example, consider the spectrum of the sun. And here it is right here. Here's the spectrum of the sun. All right. And we can tell by looking at this what our sun is made of. All right. Oh, didn't want to do that when I hit the reading. There we go. Okay. And this is what we come up with. Hydrogen. There's helium, oxygen, carbon, neon, nitrogen, silicon, iron, gold, and uranium in the sun. Here's their mass percentages. And we can tell these also, again, each of these has its own spectra, and it's in here, all right? It's in this. We can see hydrogen. We know where hydrogen's colors are, all right here. Here's some more hydrogen, all right? We can tell there's hydrogen. The darker it is, the more of that material there is, all right? The more of that type of atom. So there's lots of hydrogen. There's magnesium. You can see the sodium and the calcium. By looking at these wavelengths in the spectrum, we can tell what our sun is made of. Now, we can do this with any astronomical body out there. The problem is, on Earth, our atmosphere absorbs some of that spectrum, and it kind of messes things up. That's why it's so important to have telescopes out in space where they're not affected by our atmosphere. And recall in the notes, if you watch the notes, and if you haven't, I'm really going to encourage you to, we have atmospheric windows. And without these windows, it would be impossible for us to study astronomical objects from the ground. All right. It would be impossible without these atmospheric windows. If you haven't watched the notes, check that out. Read this stuff too. Just don't listen to me talk about it if you're even doing that. Hopefully you are. But remember, read. You'll learn so much more from reading than listening to the lecture and the notes. Finally, we end up with Section 6, the Doppler shift. Let's check out this video on the Doppler shift.
We never travel fast enough to see the Doppler effect for light, but we often travel fast enough to hear it. And so I have brought with me the world's most annoying noise on a string, and I'm going to turn it on, and then I'm going to make it come toward you and make it go away from you. And I want you to pay particular attention to what happens as the noisemaker approaches, and then as it goes away again. That's pretty annoying, right? So when it comes toward you, now, it sounds different than when it goes away from you, now. So what did you hear? As it approached you, you heard a higher pitch, and as it went away from you, you heard a lower pitch. Well, the same thing happens for light, that it gets shifted to a higher frequency when it comes towards you, that is, the light becomes bluer, and it gets shifted to a lower frequency as it goes away from you, that is, the light becomes redder. And so, what does this have to do with astronomy? Well, pretend that my right hand is a planet, and my left hand is a star. My head is the center of mass of these two objects. So the planet is out here, and the star is right here, the center of mass, very close to the star. So now as these objects orbit, they're going to orbit the center of mass, each of them. So watch what happens as they move. So you can see that the planet and the star, here comes the star toward you and away from you, and toward you and away from you. If you were to watch the spectrum of that star, you would see the star get blue shifted as it comes towards you and red shifted as it moves away from you. The very first planets around other stars were discovered this way.
Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 108. It's on the Doppler effect. You've maybe heard of that before. It's why a siren, as it approaches you, you'll hear an increase in the pitch, and then it'll actually drop off. But it also could occur if you're moving, and we'll get into that in just a second. So let's say this point here is generating sound waves. They're moving away from that point, and so if you were to listen to them, those sound waves would be hitting you at the same rate, and so it would be a constant pitch. But watch what happens if we move that object from left to right. As it moves from left to right, you can see that the waves in front of it are bunching up. What would that sound like? An increase in pitch. And then behind it, they're actually spreading out. We'd hear a decrease in pitch. You could see the same thing in water waves. The swan, we know, is swimming from right to left. It's swimming to the left. How do we know that? Well, it's generating water waves, and the ones in front of it, you can see, are getting bunched up, and the ones behind it are actually spreading out. So that tells us it's moving to the left. It also has its beak pointed in that direction as well. Now, it's not only sound and water waves, but light is going to do the same thing. And one of the greatest discoveries ever was Edwin Hubble's discovery that wherever he looked out in space, all light seemed to be shifted to the red. We call that a red shift. What did that mean? All the light that he saw was moving away from us, and that indicated we were living in a universe that is constantly expanding. So Doppler effect has these amazing repercussions. And so waves and their observed frequency will change due to motion. And let's say we've got a source of those waves, and then we've got an observer. If the source of the waves is generating waves that move out, they'll be of uniform distribution unless it's moving. So as that source moves, as it approaches the observer, we're going to see an increase in the frequency of those waves. And then as it passes the observer, we'll see a decrease. But it's not only the movement of the source, it could also be the observer. As it approaches the source, it'll hear an increase as it goes towards it, and then it'll actually be a decrease as it moves away. And so let's give me a real example of that. Let's say you're standing there and a car is approaching you. The waves as they come towards you will bunch up. And then as it moves away, we're going to hear that kind of drop off. Why does that occur? As those waves come towards you, they're getting bunched together, and so the frequency is increasing, and that's due to the change in the velocity of that object. And so you'll hear increased frequency, and then it'll actually drop off as it passes you. Now we're going to experience the same thing, however, if we're moving, the observer's moving. So analogy works good for this. Let's say we're generating some waves on the left side, so the waves are moving from left to right. So if you're in a boat, you would feel those waves hitting you. But let's say now that you're moving, so the waves are being produced, but you're moving towards the waves. Since you're moving, you're going to hit them much more quickly, and so we're going to see an increase in the frequency of the waves. Let's say the opposite's occurring. Let's say you're moving with the waves. They're going to hit you at a slower rate, so you would experience a slower frequency, maybe a lower sound if we're talking about pitch. Also applies to light, so as the light is moving away from you, all of those wavelengths will actually be stretched out, and that creates light that's going to be simply moving towards the red. If it's approaching you, it'll actually be moving towards the blue. And so this is an example of that red shift that Hubble saw. Since everything was shifted towards the red, everything was moving away from us. And so did you learn to create a wavefront diagram to demonstrate why as a source approaches you, the wave frequency increases. As it moves past you, it goes away. And also why movement of the observer can do the same thing. I hope so, and I hope that was helpful.
I think those two videos there explain the Doppler shift. Make sure you read it, and good luck with the rest of your work.